Okay. So, here we have a problem where we have a piston cylinder arrangement again, and we have two gases, air and nitrogen. They are contained in an insulated piston cylinder apparatus as shown. The thin rigid wall that separates the two chambers is perfectly thermally conducting. So, we have over here a rigid wall. So, it is rigid, that is interesting. So, which means that it cannot deform, and it is perfectly thermally conducting, which means that we would expect the temperature of these two to be the same, because if it is perfectly thermally conducting, if the temperature of the air increases, it will increase the temperature of nitrogen and vice versa. So, what we can see is that because this is a rigid wall, so the volume of nitrogen must be a constant because it is perfectly thermally conducting. So, temperature of air must be equal to the temperature of nitrogen at any given point. So, it says initially the air is at 500 kilopascal, 473 Kelvin. So, air is 500 kilopascal and T1 for the air is 473 Kelvin. The nitrogen is at 1500 kilopascal. Since we already have the temperature of air and nitrogen should be the same all the time, so the temperature of nitrogen also must be 473 Kelvin. They each occupy 0.01 meter cube. For nitrogen, this must be always the same, so that cannot change either. We are asked to find out the work and heat interaction for the air and its final temperature. So, what we are looking for is the work interaction and heat interaction. For air and nitrogen, it is given that PV is equal to 288 T and specific heat at constant volume is this. P is in Newton per meter square, it is Pascal. V specific volume in meter cube per kg, T is in Kelvin. We are told that we can neglect any internal energy changes in the partition wall. So, this wall itself essentially does not have any energy change which happens. So, that is something we are given. So, what we want is the heat and work interaction for the air. There is of course heat interaction for the nitrogen, because whenever the air gets heated, this will also transfer heat here. There is no work interaction for the nitrogen because it is rigid. So, that much is clear. So, what we have is initially the air is at 500 kilopascal and 473 Kelvin. The air is compressed. So, air is compressed down. When it gets compressed, it gets heated. Because it gets heated, it transfers heat to the nitrogen, and final pressure of nitrogen is given as 1580 kilopascal. So, what we see is P2 for the nitrogen is 1580 kilopascal. At that point of time, P2 for the air need not be the same, because the initial quantities and pressures are different. So, this is what is given to us. So, we do not know what is the final pressure of air, we know the final pressure of nitrogen. We know over here the initial volume of nitrogen and the final volume of nitrogen, because it is the same. We know the initial pressure of nitrogen, we know the final pressure of nitrogen. So, if for the case of nitrogen, we know initial volumes and pressures, we know final volume and pressure. We also know the initial temperature of nitrogen, which must be the same as initial temperature of air. So, what we can find out is using this expression, we should be able to find out the final temperature of nitrogen, which will also be the final temperature of air. So, that is what we will do. So, we have P1 V1 by T1 is 288. For both air and nitrogen, we can use this. So, let us use this for the nitrogen first. P1 of nitrogen is 1500 kilopascal. V1 of nitrogen is 0.01 meter cube divided by whatever is the mass, and T1 of nitrogen is 473 Kelvin. This should be equal to P2, which is 1580 kilopascal, into V2, which is 0.01 meter cube divided by mass of nitrogen divided by T2. So, 1580 kilopascal is what is given. So, what I want is T2 from here. So, this goes the other side. So, I get this part gets cancelled out. So, I have 1580 by 1500 into 473. Which comes out to be 498.2 Kelvin. We found this for nitrogen, but we already found out here that the temperature of the air and nitrogen will be the same at all times. So, T2 for air is also equal to this. So, we have this. So, what we can also do, if we wanted, is to find out the initial mass of nitrogen, because we know all of this. So, we know the volume also. So, we should be able to find out the initial mass. I do not know immediately whether that is required, but if needed we can do that. So, what we are asked to find out is Q, which is heat transferred between air and nitrogen, and work. So, this entire thing is insulated, the piston is also insulated. So, there is no heat transfer from outside into this system. So, if I consider air as a separate system and nitrogen as a separate system, then there is heat transferred between air and nitrogen. That is what I want to find out. But work is being done on the air from outside, that is also something which I want to find out. So, what I can do again is write the first law for both these cases. So, for air, the first law says this. For the nitrogen, the first law says the same thing, but for the nitrogen we know that there is no work interaction because it is a rigid partition. So, du is equal to del q. So, I want to find out this 1q2, which is essentially delta u. Delta u is m into Cv into delta T. I need to find out the mass of nitrogen. The Cv of nitrogen is given. Delta T I know because I have just found out the final temperature, initial temperature was given. So, what I will do is I will find out the mass of nitrogen. So, I know that P1 V1 is equal to 288 T1. So, small v is capital V by m. So, I want to find out m. So, the initial pressure was 1500 into 10 to the power 3 Pascal. Initial volume is 0.01 meter cube divided by 288, and the initial temperature was 473 Kelvin. So, I think I have converted everything into correct units. Which I think gives me a mass of about 0.11 kg. So, delta U is essentially this mass into Cv, which is given as 742 joule Kelvin, into the temperature difference. So, the final temperature is 498 minus the initial temperature is 473. Which gives me a value of 2 kilojoules. So, what we see is that the delta U for the nitrogen is 2 kilojoule, but for the nitrogen 1 Q2 is also equal to this. So, 1 Q2 is 2 kilojoules. So, we have found out that portion. Now, we can also look at the air. We know this delta Q, which we just found out here. So, if it is positive for the nitrogen, it must be negative for the air. So, we know this value. We know the final temperature of the air. We know the initial temperature of the air. So, we can find out delta U for the air. If we are finding those two, we can find out del W. So, that is what we will do. So, we also need now the mass of air. So, mass of air is P1 V1 of air by 288 T1 of air. All of these are for air. The initial pressure of air is 500 kilopascal, volume is 0.01. So, it is 510 power 3 Pascal, volume is 0.01. This is 288 and the temperature is 473. Which gives me a value of 0.036 kg, and what I want is delta U for air. What we know is that the temperatures of the nitrogen and the air are the same. So, the initial temperature is 473 in both cases, final temperature is 498.2 in both cases. Which we get as 686 joule. So, now from the first law for this air, what we see is del Q is delta U plus del W. What we want is del W, sorry, if I am writing in terms of del, I should write this as D. So, what I want is this, which is essentially del Q minus du. Del Q for the nitrogen was 2 kilojoule. So, that is heat received by the nitrogen is positive. So, for the air it must be minus 2 kilojoule. So, I will write it in joules, it is minus 2000 minus 686, which we get as minus 2686 joule, and we call this as 1 W2. So, essentially what we have is that for the air work is negative, which is what we expect because this piston is compressing down. So, for the air the work interaction is negative, because of which the air becomes hot, because of which it transfers heat to the nitrogen. So, the heat transfer for the air is also negative. That is essentially what we see. So, we were asked to find out work and heat interaction for the air, which we found out. The final temperature is also something which we have found out.